Hi, I'm Darren and welcome to Level Up EE Lab. Well, there's only two modules remaining for my HF transmitter, the main board and the power distribution module, and both of those are subjects for today's episode. Let's check them out. Let's begin with the main board and take a look at its content. The star of the show is the ubiquitous Arduino Nano microcontroller. I used one of those in my simple HF receiver project and it worked very well, so I decided to use one here. And speaking of similarities to that receiver, I'm also carrying over an SI5351 clock generator. This is another very commonly used element in amateur radio projects. See the first episode in this series to find a block diagram that shows how I'm applying it. Other elements on the main board include a MAX3232 line driver. I'm using this chip to handle RS-232 communications to and from my HF receiver for the captain and minion control modes that I described earlier in this series. Lastly, there's an assortment of other parts, such as a linear regulator to knock down the 12 volts to 5 volts, signal protection passive devices for the analog and digital inputs, and simple NPN low-side driver transistors for the digital outputs. Here's how I've assigned the nano pins to various functions. And I found a task for every single input and output, including digital pins D0 and D1. Now these are reserved for transmit and receive for the microcontroller, but in my case I need to tap into them for the MAX3232 line driver. Now I was not sure if I could leave the MAX connected while programming the Nano through USB. So I included these pin jumpers to break the circuit connection if there is a problem. If there's not, then I'll just solder these jumpers here to make a permanent connection. Next up are D2 through D4, which are connected to the encoder. D5 serves as the push-to-talk input for SSB mode and as key-down input for CW mode. Because this input is connected to the world outside the transmitter, I'm including some best practice methods to protect the input from transients and other garbage. Here's the circuit, and it's pretty much a verbatim implementation of the article in DigiKey's website regarding digital input protection. This combination of Schottky diodes, resistors, and caps should provide satisfactory protection. Moving on, I'm using D6 and D7 as digital outputs to command 12-volt relays elsewhere in the transmitter. D6 controls the single sideband audio stage power relay, which supplies 12 volts to the microphone amplifier and balance modulator only when in single sideband transmit mode. That relay is located on the power distribution module. D7 controls the antenna relay, which switches the antenna connection between the external receiver and the final power amplifier. That relay is located on the antenna module. Neither of these drive the relays directly, but rather through simple transistor switches using the very common 2N3904. D8 and D13 are assigned to the display, which sure is a pin hog. I do not need the MISO function, so D12 sits unused. Moving over now to the 8 multipurpose pins A0 through A7, I found uses for all of them. A0 is used as a digital output to switch on and off the side tone audio oscillator on the power distribution module. More on that later. A1 is yet another pin gobbled up by the display. A2 is used as an output to turn on and off the final amplifier FET bias voltage. A3 is used to receive an analog signal from the bandpass filter module. I'm using a resistor divider on that module to tell the Arduino which bandpass filter is installed. This is the exact same method that I used on my HF receiver. A4 and A5 are the I2C serial bus connection, which I'm using to interface with the SI5351. And lastly, A6 and A7 are used to receive the variable voltage forward power and reverse power signals determined by the directional coupler on the antenna module. I'll be using those signals to calculate transmitted power as well as SWR. Here's the 3D rendering of the main board, including block-up models that I created of the Nano and the SI5351. It measures 65 by 81 millimeters and is fairly unremarkable. I did push the 5-volt linear regulator to one corner to get it out of the way and used 9 vias to stitch the ground planes underneath it for good heat conduction. And here it is, all built up. Yeah, I had the bare board fabbed. There's just no way I can etch at home a TSOP16 pattern and expect it to be hand solderable. You really do need solder mask. I did decide to socket the Nano only because I was paranoid that I might accidentally fry an input or output, and I wanted the ability to replace it easily if needed. I mentioned in earlier episodes that I had plans to use tilt switches on this design to detect whenever I changed the orientation and then have the screen rotate automatically. I had to axe that idea because I needed all those inputs for the other features that I just went through. Now, it's really not going to be that much of a pain or an inconvenience because I don't think I'm going to change the orientation that much, and having to go into the menu to adjust it is really not that big of a deal. And if I had other features that ended up on the chopping block, then I might have gone with a multiplexing chip and enabled all those. But really, that was just one extra feature that I couldn't enable, so no big deal. Now let's switch over to the power distribution module, which also includes an integrated side tone generator. The basic function of this section is obvious. It's a star topology for the 12-volt power and grounds for the entire transmitter. I decided on this star approach when I was sketching up a wiring diagram for the transmitter. Most of the boards need 12-volt power, and I could have just daisy-chained all of their power connections together, but that likely would have caused problems. In particular, ground references could be different between modules due to accumulated voltage drops, and having higher power currents going through more sensitive circuits could have created noise or offset issues. So having a star power and ground helps minimize those issues at the cost of a bit more wire length to make all the home run connections. Also on this board is the SSB audio stage relay that I mentioned earlier. It's controlled by digital output D6 and only applies power to the microphone amp and balance modulator when the rig is in single sideband mode. In CW mode, I don't want speech or other sounds that are picked up by the mic to be mixed in with the CW carrier. So the simplest thing to do is just power down those stages when I'm transmitting CW. I chose to do that by using a relay, but a PNP transistor or a MOSFET could be made to work just as well. Lastly, this board also contains an audio tone generator that makes a fixed frequency tone when sending CW. This is called side tone generation, and it's commonly done on CW transceivers. When you've tuned your receiver into someone's CW transmission, what you hear is very close to a sine wave. That's just the natural result of the conversion process. And when you send your reply, you'd like to hear your signal match in tone quality and in pitch. Now, this is a bit harder to do well than you might think, meaning there's a ton of ways to generate crappy sounding audio tones. And at the crappy end of the spectrum, we find lots of circuits based on the common 555 timer. This is a very poor choice here because a 555 is a digital timer, which means the signal you get is a square wave or some form of a sawtooth or triangle wave, depending on the circuit design. What we want for a pleasing tone is to generate a sine wave at a single frequency, typically 600 Hz, although some hams do prefer a slightly higher pitch. And an integrated circuit is really not necessary to generate a high-quality sine wave. It can be done with a single transistor and a handful of discrete parts. Case in point is the design shown by Mike Maynard on his website at k4icy.com. It uses a single NPN transistor along with these caps and resistors to make an audio oscillator. This specific topology is called a twin T oscillator and is commonly used to generate a fixed frequency high-quality sine wave. The frequency is determined by the combination of these resistors and capacitors. The values shown here generate a nominal frequency just under 600 Hz. C1 and C4 need to be the same value, and the capacitance connecting R1 and R4 to ground needs to be double that value. That's easily done by using 4 caps of the same value and paralleling 2 of them like I've done here with C2 and C3. I'll come back to this FET in a second, but let's jump to the right-hand side where we find the very common LM386 being used to amplify the signal. Nothing unusual here. I'm using C15 and R11 to set the gain. I'm only driving a 1/4 watt speaker, so I really don't need that much power. Now back to that FET. One of the other challenges for making a pleasing CW side tone is to turn the audio on and off smoothly. You don't want abrupt transitions, that will sound clicky. And even worse things can happen if you just switch the oscillator power on and off. That will likely cause slight changes in pitch as the oscillator starts, which leads to a chirpy sound. What needs to be done is to smoothly turn on and off the signal going into the amplifier. And that's where this FET along with R6, R7, and C7 come into play. Those work together to smoothly charge and discharge the FET's gate voltage, which then smoothly changes from shunting the oscillator output to ground to allowing it to pass unimpeded into the LM386. Let's take a look now at an LT-Spice simulation of this circuit. I've simplified the schematic to just an impedance load resistor for the LM386 input. I don't need the 386 for this simulation. But I've added these components over here on the left. This is a simplification of the circuitry on the main board where the Nano will digitally turn on and off the 2N7002 FET. And zooming in on the simulation results, we can clearly see smooth on and off transitions. Now, because these transition times are controlled by discrete resistors and caps, I've got some flexibility to tune them if I want by changing those values, but for now, this looks pretty good. Here's a quick view of the 3D rendering of the board layout. Nothing particularly remarkable about it. There really weren't any challenges to overcome to make this design. And here it is all populated with the speaker installed. Like the main board, I also had the bare board fabricated. In this case, because I want robust plated through holes for all the power connections. It's likely I'll need to solder and unsolder those a few times, and my home-built boards don't hold up to that very well. I designed and 3D printed this two-piece bracket assembly to hold both the board and the speaker firmly in place inside the case. The speaker is one that I had in the good old junk box. Nice to press it back into service. Okay, so how well did I do? Let's give a listen to the sound quality. I'm using a simple program in the Nano to send a pretend CQ. Not bad at all. I think this will work just fine. So that's it for today's episode. I do hope you enjoyed this material. Looking ahead, I'm down to the last few episodes on this build, the RF power amp, the software, and then debugging and getting it on the air. So I hope you stay with me to the end of this ride. So until next time, bye for now.